Hello and welcome to the presentation of functions and their graphs. Functions are the major objects we deal with in calculus because they are key to describing the real world in mathematical terms. This video reviews the ideas of functions, their graphs, and ways of representing them. In each case, the value of one variable quantity, which we might call y, depends on the value of another variable quantity, which we might call x. Since the value of y is completely determined by the value of x, we say that y is a function of x. Often, the value of y is given by a rule or formula that says how to calculate it from the variable x. For instance, the equation a equals the pi times r to the second power is a rule that calculates the area a of a circle from its radius r. A symbolic way to say y is a function of x is by writing y equals the f of x. In this notation, the symbol f represents the function. The letter x is called the independent variable. So this is the independent variable and represents the input value of f, and y, the dependent variable, represents the corresponding output value of f at x. So this is the dependent variable. The set D of all possible input values is called the domain of the function. So big D means the domain of the function, and this is the all possible input values. So the all possible input values, and the set of all values of f of x as x varies throughout D is called the range of the function. So R stands for range, and this means the all possible output values. So all possible output values. Think of a function f as a kind of machine that produces an output value f of x in its range whenever we feed it an input value x from its domain. So let me show you how this works in a childish way. We got a bag here. This is the domain bag, and there are numbers inside and numbers outside of it. Now we got a machine here. This is called the f machine. This will represent the f function. And here is another bag, and this is going to be our range bag. Now whenever I feed it with a number from inside the domain bag, for example x, I get an output value, the f of x. So this is going to be the independent variable, and this is the dependent variable. Now if I feed it with an x from inside the domain bag, I'll get an f of x that will fall into my range bag. So this is going to be an element of my range, and whenever I try to feed my machine with numbers outside the domain bag, it will indicate an error because I cannot feed it with numbers outside the domain bag. Now let's see an example for this. So consider f of x as x over x. Now you may say that, but why don't we simplify it? Because there is a same exact thing in the numerator and the denominator, and something divided by itself, it's just 1. You're almost right, but no, because consider the f0, so the f of 0 case, because then this is going to be 0 over 0, and we know that we cannot divide by 0, so we cannot make the simplification because of this. So 0 won't be the element of our domain. Let me show you another example. The square root x key on a calculator gives an output value, the square root, whenever you enter non-negative number x and press the square root x key. The output value appearing in the display is usually a decimal approximation to the square root of x. If you input a negative number, then the calculator will indicate an error because x is negative, and it's not in the domain of the function and cannot be accepted as an input. The square root x key on a calculator is not the same as the exact mathematical function f defined by the f of x equals square root of x, because it is limited to decimal outputs and has only finitely many inputs. The domain of a function may be restricted by context. For example, the domain of the area function given by a equals pi times r squared, like this, as you can see here, only allows the radius r to be positive. When we define a function y equals the f of x with a formula, and the domain is not stated explicitly or restricted by context, the domain is assumed to be the largest set of real x values for which the formula gives real y values, the so-called natural domain. So the natural domain. If we want to restrict the domain in some way, we must say so. The domain of the y equals x squared is the entire set of real numbers. To restrict the function to, say, positive values of x, we would write that y equals x squared and x is bigger than 0. Now we are going to play a little game. I just need some more space. That's it. Now verify the domains and the ranges of the following functions. So I will write up functions, and those are going to be the y equals x squared, and y equals 1 over x, y equals the square root of x, the y equals the square root of 4 minus x, and the last one is going to be the y equals the square root of 1 minus x squared. So these are the functions. And verify the domain, so the x values, and the range, so the y values or the input, the output. Now let's start with y equals x squared. So the formula the y equals x squared gives a real y value for any real number x, so that the domain is minus infinity, from minus infinity to plus infinity. So it will look like this. And the range of the y equals x squared is from 0 to infinity, because the square of any real number is non-negative, and every non-negative number y is the square of its own square root. But we are running out of time, so I will continue this exercise in the next video. I hope to see you soon.